Good morning or good afternoon, everybody. Hope everybody is safe and sound. I'm Jack Field, the Keysight Design Software Midwest Manager, and I'll be your host for today's virtual seminar entitled Reducing Electromagnetic Interference in Switch Mode Power Supplies, brought to you by Keysight in partnership with ElectroRent. Now let's move on to the presentation. There will be a break halfway through, and we will have polling questions to break it a little bit. There will be a presentation as well as demos. Joining us today is George Crumrine. George has been a field application engineer with first HP, Agilent, and now Keysight since 1989. His experience includes design and analysis of RF microwave circuits, receivers, amps, systems, and antennas. He is also experienced in the areas of radar, electronic warfare, signal integrity, and high-speed digital channel design and analysis. He currently supports the simulation and analysis products from Keysight's PathWave Design Engineering Software Group and holds a BSEE from the University of Cincinnati. Welcome all, and George, you now have the floor.
All right, thank you, Jack. And thank you, everyone, for attending. I will, so we should be on slide 2 here, describing electromagnetic interference. And what we want to try and get is there is a very nice new power electronics cockpit called PE Pro, Power Electronics Pro, for the purpose of looking at switch mode power supply, conducted and radiated EMI. It does many other things, but wanted to focus a bit today on EMI. So from that perspective, I wanted to make sure that I have an understanding of what we're talking about with regards to electromagnetic interference. And there's a aggressor, something that is generating the interference, and then there's a victim. In our case, what we're looking at here is how do we look at this particular product as an aggressor. And so it has to pass some compliance, which we'll talk about later. And we need to measure how much interference it's generating, both conducted and emitted or radiated. And so we'll see a little bit more detail about that as we move along. So it should be on slide 3 here. And with regards to switch mode power supplies, the electromagnetic interference challenge with them is these are inherently noisy. They have a switching frequency, a fundamental frequency. In this case, the plot you're seeing here is similar to the one I'll be showing you later. The plot we're looking at here is running at 2 megahertz. And you see that as that peak near the center, just left the center. And across the frequency spectrum, of course, a lot more noise components associated with that, harmonics, subharmonics. And in addition to this fundamental switching frequency that the device is running at, there are parasitics associated with the layout. And today's modern, high-speed, fast switching supplies are generating a lot of extra noise and suffering from a lot of the parasitic effects of the layout due to the fact that we have these very high frequency and high switching speeds associated with their performance. So parasitics in the layout are important to consider, and that's what we want to focus on as well. On slide 4 here, we have a quick look into we'll see in more detail later, but this is the test bench. One of the test benches is a conducted EMI test bench. And some of the information we can pick up from within there. Frequency domain, time domain plots, as well as the ability to plot surface current densities and radiated emissions. One of the things that will make this very nice and convenient is what you're doing is running an analysis in a virtual chamber, and you're generating the results from a virtual prototype. So you're looking at, before you build the product, how I will be able to predict and what kind of nominal results I can expect from this artwork and component configuration before I build it. And that's what we refer to as a virtual prototype in this virtual chamber. Slide 5 here is a little bit of attention to the switch mode power supply itself and why today's modern high-efficiency power supplies are suffering from some of these issues. So the idea is we want to shoot for super high efficiency. And not only that, but we also want to try and make sure we're keeping things as small as possible, keep the weight down, and especially for airborne applications as well, it's even more important. But imagine that you spend, in an automobile environment, you spend a lot of time and energy focusing on keeping the vehicle structurally strong and still lightweight so you can get a lot of good mileage, as well as be super efficient in maybe an electric vehicle. You've got an enormous battery pack, and you spend a lot of money to charge that battery pack and design it. And then you have inefficient power converters that are throwing that energy away in terms of inefficiency. And also, where there's inefficiency, then that means there's heat being generated, and you have to have a heat sink. And on an automobile, unless it's in the middle of winter in Fargo, there is no cold plate on the car. So keeping things efficient means we can keep heat sinks smaller.
As I was talking about with regards to the power supplies, we're shooting for high efficiency, and in the process of gaining this extra efficiency, we pick up a huge benefit that we're not throwing away heat. We don't need a big heat sink. We can save weight and size. And we refer to this as, and to do this, we need high frequencies and we need fast switching edges. And we refer to this as the high DIDT era. And the DIDT issues come into place somewhere in the area starting around 1 amp per nanosecond. So if you look at the bottom left portion of the V-spike equation there, you've got LDIDT. So imagine that you're slewing 10 amps, and you've got 2 nanohenries of parasitic inductance, which is a small number, actually. It can be significantly higher. That's already 20 volts of spiking. And this not only generates noise, and which can also by itself be a problem, but it's going to perhaps damage components. And these are small numbers at this point. So, and then for radiation, we also have to keep a control over the size of the layout and the trace content so that we have this all in mind. So let's keep going on the subject of the power supply itself. Slide 6 here describes some of the issues with these fast edge speeds, high DIDT. As I said, we want something that is lighter, more efficient, smaller. And in the past, what you've done, and I've been with companies in the past and worked with them that would literally build a product and try it out and then maybe go through 3 or 4 iterations of board spins to try and fix some of these issues. And my colleague, Colin Warwick, refers to this as the solder and see mechanism. And this design flow is slow, it's expensive, And it doesn't really give you a way to decide, did I really fix the problem I thought, or was it an accident? So with this power electronics cockpit that we're describing today, we want to do something after we do the layout, but before we build it. And that allows us to do virtual spins of the layout, virtual spins of the board, as well as maybe replace some components or swap different components and see how things are going. So, quick view at the power supply. This is a really, really simple example of a hard switching step-down converter, which is referred to as a buck converter. On the far left, you have a voltage source. We'll just say it's a 12-volt car battery, for instance. And then we have a switching device, which is some transistors. We have an energy storage inductor and capacitor, and the L1 and C1 form a low-pass filter so that this switched square wave with some duty cycle is then filtered by the LC network so that all I get at the output is my DC that I want. That's the ideal presentation. This is the way it should work. Now, if I can, in order to get this inductor and this capacitor smaller in size so that they're less expensive and don't weigh as much, I can take the switching frequency and move it up. If I move the switching frequency up, then that means the cutoff frequency of the LC filter can be higher, which means I can use smaller parts. Smaller parts, hopefully, will save me some money and some weight. Audio check, Jack. Does everything seem okay?
Yep, just great, George. Thank you for asking.
Well, nothing if not polite. So on the left here is the low-frequency switcher with relatively low slew rate edges. And we've got a calculated switch loss of a little over 3%. The middle plot, we've gone to a higher switching frequency using the same slow edges, and the switching loss is over 15%. And the issue here is, in order to reduce the loss and be efficient, it's not good enough to just raise the switching frequency. We've also got to pay attention to the edge rates. So, again, we're trying to get efficiency in order to reduce the size of the heatsink, save weight, and also just be efficient, not throw energy away. If I'm not switching the transistors on and off properly, if I'm not switching them fast enough, I want this edge speed to be such that the two transistors in a half wave or the four transistors in a full wave are switching fast enough so that everything's switching synchronously and fast enough so I don't have one leg on while another leg is still on. If I don't do this right, if any of you are RF amplifier people, you know the efficiency is a function of how I can get these transistors to switch so that I've got the conduction states exactly the way I want them. So this is where some of the problems have come up, where people are using faster edges, and with the faster edges, that LDIDT is creating voltage spikes because the parasitic inductances haven't been accounted for. Switching to slide 9. One more thing to keep in mind, and this will be our last sort of specific attention to the switcher itself, the switch mode power supply. One thing to be aware of is, in this case, a 2 megahertz switching frequency. These trapezoidal waveforms, rectangular waveforms, have a significant amount of harmonic content. And And that goes into a very high frequency realm and begins to cause problems at the RF frequency bands. In this case, the example you're seeing here is a 2 megahertz square wave, duty cycle 50%. Now, we just assume here approximately a 4 nanosecond rise and fall time. And if you look at the waveform on the left, the red trace with 2, blue trace has 5 harmonics, the purple trace 10, and then the cyan trace has 50 harmonics. And even with that many harmonics, it's not a perfect square wave, but that square wave with those 50 harmonics, or approximate, shows up at this, on the right, as this spectrum. So this could go well into a couple of hundred megahertz, which is RF territory, where significant amounts of interference could occur with other devices. Now, what we would nominally expect to see is approximately a 20 dB per decade roll-off. And somewhere around the line of, if you look at that roll-off, if we were able to zoom in on that plot, you'd see that there is an additional roll-off, and that frequency point is referred to the 6 dB cutoff, the knee frequency, and this is associated with the switching edge, the rise and fall time. So there's 2 frequency components, the switching frequency and then the edge rates. There's a number of things that go into this knee frequency, but some of them depend on the shaping of the pulse. But nominally, roughly about 4/10 or 5/10 over the 10 to the 90, 2080 rise and fall time would get you the 6 dB point. And that's a cutoff where you're looking at 6 dB below where the 20 dB per decade would be. This is just to keep in mind, there's 2 frequency aspects, the switching frequency and then the rise and fall time associated with the edge rates. All right, back to the topic of EMI on slide 10. So we have intended operation. That's your phone has a Bluetooth component to it, and that's something it's supposed to be able to do. And other things nearby should be able to tolerate that as interference. And then there's unintended transmissions where it's spraying out content that it's not allowed to be, and it's not reasonable to expect other products to put up with it. So that's why the FCC and international organizations are strict about this. So we'll talk about radiated and conducted, but we'll first look at conducted. And if this thing is plugged into a source, such as a battery or some other power supply upstream, some of this EMI content can conduct to the source, and that can be a problem in itself. Slide 11 describes some of the different continental regulatory agencies in the United States, of course, the FCC. And then, in a general sense, we see a lot of what's referred to as a CISPR regulations. That's CISPR. And I took enough Latin to know that I shouldn't try and pronounce French. So I won't try and pronounce the name of it. But it's a special committee, a European special committee for radio and electronic interference. And it's broadly adopted with many different standards for different application areas. We'll talk today very specifically about CISPR 25, which is automotive. But you can see there's regulatory agencies in China, Japan, Europe, United States, and everybody has a voice, and they're very specific about operation in their realm of authority that these products have to conform to. Here's some standards for CISPR and the application area and some relative correlation to the FCC numbers. And on slide 13, we start to see the first glimpse of how we're going to run some of these measurements. And in a chamber, this becomes a challenge because chambers are expensive to build and to maintain and to operate, and they're like ice rinks. Everybody wants to be in there at the same time. So if you ever try and organize a youth hockey team, you'll find out the only time they have for you to practice is at 3 in the morning. You don't want to be in the EMI chamber at 3 in the morning. It's actually, I've done it. It's not fun. But the things that are an issue here are from one chamber to another, you need to make sure you have some consistencies in the setup. So the equipment used, the location, the configuration, and these are all part of certifying the lab. And point being that at some point you will have to go into the chamber and make your measurements to get your type certification, but why not do this as much as you can in the simulation environment before you get there, just to have a good, confident feeling that you have a deterministic analysis done and you're confident that your EMI standards are going to be met. To do this in the simulation environment, we need to model as well as we can the test bench aspect. We can't do everything, but we can do as much as possible, and we need to pay attention to some of that. On slide 14, you should see on the left, you've got a little correlation between simulation and measurement for some voltage spiking. And this is not extremely difficult for general purpose EDA tools, but what Keysight has as sort of a unique capability is the ability to excite the PCB under operating conditions and then see how it behaves in the electromagnetic environment under operating conditions. So we refer to this as insight, where you're looking at things like on the right, you should see an animation of the surface current density on a couple different layers of a PCB. And refer to that as insight. That gives you the ability to look into a structure, gather a behavioral understanding of what's going on, and then is it doing what you thought? Is there information there that you can visually pick up or measure to give you an idea how to fix problems and what approach to take? It's not going to tell you how to fix something, but it will give you insight as to how to fix it. So on slide 15, we're looking at the emissions compliance tests on the left, radiated, and on the right, conducted. Radiated tests will be generally described in terms of electric field strength. There are different units of measurements that are used depending on the application and the regulatory agency. The thing about radiation is if you ever look at an electronic device you got at Christmas and you open it up, there's a little tab in there somewhere with a little piece of paper with some fine print. It says, if you're experiencing interference, move it away from the interferer. That's about the only way to solve some problems. And that's because radiation is an exponential versus distance loss. Another approach to radiation is shielding. You see that a lot. If you open up your phone or computer, you see a lot of shield cans in certain locations, and that's sometimes a very effective approach. As far as conducted emissions on the right, this is where the interference is moving along the actual connection circuit cable, so a power cable or a USB cable. So conduction through the cable itself, and the measurements there are a little bit more straightforward to understand, but they can be a little bit more difficult to make a measurement of because you have to isolate this device you're testing from the measurement source. We'll talk about that shortly. And then at the bottom, you have some, in blue there, you have a conversion table for the different units of measurements. On slide 16, going back to the traditional approach, building a device, fixing it, respinning it. Cut and try approach, starting with a schematic analysis and some type of measurement setup, a lot of care and attention, a lot of repair and rework, and build again. Expensive and slow. Get into the chamber and spend some money, go home, fix the chamber again, spend some more money. Did I mention this might be stressful? So what we're advocating, and we've got some case studies. In this case, this is a power factor conversion, a three-phase power factor conversion module from ST Micro, where they actually got it right on the first pass. And this is not uncommon. If the engineering group that you're part of applies some regimen and some learning with a little bit of experience in the use of the tool, you can get things right on the first time, and people do this. And sometimes you have to, for no other reason than you don't have time. You don't have time for a second spin. Even if you have the money, you don't have the time. So our idea here is let's do this in a virtual environment where the layouts are done in the computer, a virtual analysis in a virtual lab, a virtual chamber, and then any readjustments, rework takes place on the computer. A couple things that are important to understand, especially with regard to the EMI conductive measurements, are differential and common mode noise. I think a lot of people would agree that the differential noise is easier to understand than common mode noise. The currents are flowing in opposite directions. By describing them as differential, you're indicating they are out of phase. And this is very normal behavior. And some of it's actually due to component parasitics, but a lot of it's very normal behavior. Common mode noise, on the other hand, is where the currents are flowing together in phase, and it can be very difficult to actually make this measurement and trace it down. And one of the real big causes of common mode noise is the actual physical parasitics associated with the layout, the actual artwork. So we'll need to talk about this a little bit more. Now, I want to try and make sure we don't try and dial in too deep here on this slide 21, the origins of the noise modes. The point here being on the left is a differential noise description where all of the noise current is flowing in a loop. And on the right is a common mode noise configuration. And what's important to understand, if you look at the right side and you look at load Z2, that would represent what you might describe as your ground plane or your reference plane. And if that is 0, then you have a perfect ground plane. And you have no losses, and the voltage potential anywhere on that plane is 0. In addition, if you look at the termination Z3 and Z4 on the source and the load, left and right, if those termination impedances are also 0, then again, you've got perfect ground references at your source and load. So the way to get this common mode perfect condition is if you have these Z2, Z3, and Z4 are all perfectly 0. And this is commonly done in a SPICE type of simulation. The problem with that is it's a bad assumption, because those terminations and that ground plane are never going to be perfect. So when we refer to a schematic-only situation, we're referring to a configuration where you're running maybe a SPICE analysis and you haven't associated any layout parasitics with the analysis yet. I've switched to slide 22. So here's a schematic setup, an initial schematic analysis configuration and a SPICE schematic that would show a buck converter, a step-down converter. I've got a half bridge, 2 FETs. And what's wrong with this schematic? And I've showed this to various customers and say, you know, there's nothing wrong with this schematic. It's perfect, and that's the problem. It's too perfect. All of those wires, all of those connections are perfect connections. They have no physical attributes. There's no loss. They have 0 length, 0 time delay, no parasitics, no capacitance, no inductance, no resistance. And you can't build this. So you have to take these components and place them on a layout and connect them with traces and copper pores, vias and interconnects in different layers. And once you start doing that, then these wires no longer become perfect. They start to pick up parasitic physical behavior. So just running a SPICE analysis is important, but it's not good enough. You have to start somewhere, and this is a perfect place to start, but you also have to realize that at some point you've got to go to layout and physical attributes will come into play. Switching to slide 23. This is a example of some screen caps of some noise behavior in it's described as a compliant design. On the top left, I have the residual voltages on the battery, lead, and ground wires. Bottom left, this shows the noise voltages broken out into common mode and differential mode components. Now, if I take you in strictly a SPICE environment, that common mode noise will probably not be there because you've rep your ground planes as ideal. So the reason we're picking these up is this is a layout-based analysis. On the right side, we've actually gone into the circuit, and we're looking at one of the FETs, and we're on the source of one of the FETs, and so it's no longer the same ground reference, maybe as the leads coming into the device or going out to the load. You can also see some spikes. So the switching spikes are correlating with the common mode noise, and the sine wave type behavior is correlating with the differential noise. We'll look at this a little bit more detail later. A different design, but this content. Slide 24 is, as I mentioned just a few slides ago, if I'm on a perfect schematic environment, then you can see top left, I've got no common mode noise because the ground references are all ideal. So it's non-fault. And on the right side, when I add the parasitics associated with the layout, the scaling's the same from left to right. I'm picking up common mode noise. That's the red trace referenced on the right y-axis. And then the other thing that happens when this is seen is now you start to see ground bounce effects. So we'll talk about that. All right, moving on, slide 25. When we do these conducted measurements in the chamber or in the simulation environment, we want to just separate our differential and common mode noise. And we need something special to do this. It's called a listen device, line impedance stabilization network. This is a special piece of instrumentation, and we'll set this up in the simulation as well. Its job is to separate the source from the device under test, the electronics under test, keeping the noise or any noise that's conducted out of the device under test from getting onto the power source, but also to provide a standardized measurement tap point so that I can connect an analyzer and everyone can agree that from my certified lab to your certified lab and from my simulation setup to your simulation setup, I'm actually tapping into a standardized point of reference to pick up this noise. And in the lab, when you make the measurements, when you see noise, you typically will see the composite noise, which is the differential and the common mode combined. What's nice about the simulation environment is I can separate the two. That's simple to do and very convenient to do, and gives you a lot more insight as to what's going on. If you look on the far left, the blue trace, that's the differential noise measurement, and you can see there the switching frequency fundamental very clearly. That's the sine wave and the time domain waveform on the bottom right. And the common mode noise spectrum in the middle, the green, that fundamental isn't there, but you have a significantly higher high frequency content. If you look at the right, the very far right, the composite noise, you'd never be able to separate that. They all look the same. So separating this in the simulation environment is convenient and very helpful as you decide what approaches to take to resolve the issues. So this is our first look at the test bench. Slide 27. The test bench gives us an opportunity to bring in the artwork or create it ourselves, run the analysis, and then attach this standardized load source and this listen network with a spectrum analyzer, a virtual spectrum analyzer, and then look at the results. If any of you have used ADS, the Advanced Design System, before, on the far left you see the cockpit window, and we'll open up the schematic with the EMI test bench. And on the right, you see the test bench itself. We'll look at this live in just a few minutes. And this particular example has, on the very bottom, in the middle, is the model. So it has input voltage source and output load connections. And then connections to the test bench. You've got the listen network itself, the load, some special configurations for running the time domain analysis and converting it to frequency domain. And then in addition, we've also got the parasitics associated with the lead connections for the EMI chamber type of configuration in there as well. I'll show that to you in a live demo. It's a little hard for you to see that on the slide there. Okay, so I'll switch to a demo. I'll come back to this GDK model. It is a common mode choke, and I'll talk about that in a little bit. But I wanted to show you the ADS cockpit first. This is the schematic of a dual FET buck converter. I've got controller network, which is running the duty cycle control to give me my output. Driver, FET pairs, some loading. I've got an output, storage capacitor, and inductor. And then this is an ideal schematic. It is a representation of the starting point. No physical parasitics associated with this yet. Oops, sorry. Wrong display. Here's some results, and before I talk about the results in any detail, I want to show you the layout. So it's a fairly simple layout. It's 1 ounce copper top and bottom, 2-layer. And it's a pretty small, it's a little module. It's smaller than an inch square, about 3/4 by a 1/2 inch. And if I include all the parasitics associated with this layout extraction, then here's one of the results I can study. And this particular result is I'm ramping up the input supply, which is a 20-volt source. And then my output regulation is set at 5 volts. So just looking at, on the top trace there, the blue is the input, the red's the output. You can already see a significant amount of noise is present. And if I zoom in on one of the internal FETs, 100 microsecond zoomed in on the bottom, you can see right just before 50 microseconds where this feedback loop is locking up. So let me put that away. And if I take that artwork and I bring it into this, come on. Sorry about that. The sharing seems to be sort of grumpy with my graphics, so I won't move it around too much. But I've stretched the board out by a factor of 2 so you could start to see inside of it a little bit. And in this cockpit is where the electromagnetic analysis is performed. The layout is rigorously solved, all the metal, and this is thick metal configuration, by the way, it's 1 ounce copper top and bottom. And then all the vias, it's assumed that every piece of metal interacts with every other piece of metal. So it doesn't make any assumptions. And then this data is then handed to the circuit solver, and the circuit solver says, okay, I now see how everything's connected. I'll give you the answers. So this is what we'll do a little bit deeper dive on later when we do an EMI and a radiated analysis. So I will stop sharing here. Where's my console? So slide 30. Is that showing up, Jack? Slide 30 now?
It is. Measuring conducted
Great.
emissions.
Yep. All right. Bear with me a few more slides and we'll take a break. As I mentioned earlier, there's this thing called a LISTEN, a line impedance stabilization network. This is a significant portion of the measurement standards. And so essentially it's a high-pass filter. And it has some very tight tolerance components in it. And its idea is to present a uniform standardized tap point to make my measurements, but also to separate the electronics under test from the outside world. It gives me a very solid, repeatable, known impedance. And the idea here is that if I put one of these in my lab and you put one in your lab, they will behave the same. So I should get the same results in 2 different labs. We need to make sure we're modeling that in the simulation environment. All right, time for another poll question. And I missed the question. Where is it? Oh, there it is. All right. Now, don't overthink this, but if you have a PCB, 1 ounce copper plating, let's consider a 4-inch wide power plane. What would be the equivalent American wire gauge AWG size? Don't overthink it. Don't go off and calculate it. It's not a difficult calculation, but I just want to get a perspective. And I personally was quite surprised when I did this. And I'm going somewhere with this. This isn't a random question. So again, 1 ounce copper plated PCB, 4-ounce power plane. What's the equivalent wire gauge size? Yeah, so part of it is, it's a little bit of a trick question if you don't know wire gauge sizes, and some people have a pretty good feel for them, and some people don't. But a 20 gauge was my guess when I first saw this question, and the correct answer is number 12. And you think about 12 gauge wire. 12 gauge solid wire is about the last solid wire gauge you can actually conveniently bend with your fingers. You know, it's a pretty good sized piece of wire. It handles 20 amps in a household circuit, 50 feet long. And it's shocking to me that a 4-inch plane of 1 ounce copper is equivalent to a 12 gauge wire. So what this means is when you look at these power modules and these power distribution networks, 1 ounce copper can carry a lot of current without struggling at all. So, so keep this in mind. We'll have another question later related to this. All right, slide 32. This is the line impedance stabilization network. On the right-hand side, you see its frequency-dependent behavior. I described it as a high-pass filter. And inside, you have some, as I mentioned earlier, some very tight tolerance parts. And you want them to be tight tolerance because you want to make sure that everybody's version of this is the same. And if you don't have the tolerances right or tight, then you will also have an issue with regard to separating that common mode and differential noise. Now this tap point here in the middle, pin 4, is where the measurement will take place, the conductive measurement. A couple more things to consider. In the chamber, we're going to use a spectrum analyzer, which is a tuned radio. In the simulation environment, we have to come up with a way to simulate the measurement behavior of a spectrum analyzer. And the simulation is going to be a time domain simulation. So we have to be able to take that time domain simulation. We need to run an FFT on it. And then we need to process that frequency domain FFT data as if it were made a measurement by a spectrum analyzer. So the spectrum analyzer that's making the EMI measurements in the chamber is a tuned receiver. It has a frequency span that it will run over, and the regulatory standards will describe how to make that measurement. If you look at the bottom right, the CISPR standard for the different frequency bands describes different measurement bandwidths and frequency ranges associated with them. In a spectrum analyzer, once the signal's down converted to IF, it's run through a filter, resolution bandwidth filter, and this is done to, there's a aspect of being able to decide if two signals are close in frequency, how close do they have to be before I can't see them anymore as two different signals? And that's what the resolution bandwidth does. It decides for the receiver how close the receiver sees two signals before not knowing that they're two separate signals anymore. So there's this concept of narrowband and wideband. And in the simulation environment, we have to, and we do, we've got this set up in the test bench in the post-processor. We do this for you automatically. We set up the receiver, the simulated receiver, to give you results as if they were associated with this standard. Now, the other thing, not just the resolution bandwidth, but also the detection method is an important aspect of these EMI measurements in the lab. And again, we have to be aware of this so that in the simulation environment we can replicate this behavior of the this signal analyzer. So there are a couple different methods: average, peak, quasi-peak. If you look on the right, there's a little description graphically of the average value of a pulse signal, peak value, and then what's described as a quasi-peak. And in the simulation environment, we need to be able to replicate this as well. Now, one of the things we don't do in the simulation environment is we don't do the quasi-peak because the quasi-peak is used for aperiodic signals that take place over 4 or 5 seconds, 2 or 3 seconds. The simulation that we're going to be running will rarely be longer than a second worth of time. We get to steady state, and I'm not going to run any longer than that. So quasi-peak's not associated with the simulation environment, but that's okay because it has its own different perspective for the measurements. A little bit more detail on the next slide for your reference, slide 35, just gives a little different description, a little bit more description between the 3 detection methods. And if we didn't say so earlier, all of these slides will be available for you to download at your convenience. And also if I didn't say this earlier, the example that I'm showing you is built into the product. So if you did have ADS already or you chose to run an evaluation of it, this example is built into the product. All right, so in the effort of running a simulation of electromagnetic interference, electromagnetic compatibility, the idea here is I want to find this problem before I build the product. I don't want to spend a bunch of time and money fabbing parts and going into the lab and making more measurements. So we refer to this as a virtual prototyping environment, a virtual measurement environment. All right. Second question. 2 more slides and we'll go to a break. Why are parasitics so important? Number one, in this, as I referred to earlier, this high DIDT era, LDIDT is going to kill us when the current slew rate is in the 1 amp per nanosecond time frame. These parasitic inductances are easily going to be in the 1 plus to 4 or 5 nanohenry range, and under those conditions and these higher switching frequencies, and you look at this plot here, this is a 2 megahertz switcher, those harmonics and those edge rates and those parasitics in the layout are going to cause a lot of higher frequency noise content. In addition, you have 2 different sources of these issues, the components themselves and the layout. The component parasitics we'll talk about after the break, and the layout parasitics after the break as well. And as a engineer, what are engineers good at? Trade-offs. So trade-offs will probably have to be made. Some of the things you can easily accommodate, some of the things you can't. So there's a price involved, there's time involved, and there's also physical aspects in terms of maybe I just don't have the opportunity to move things around or change the size of the board as I'd like. So there's going to be a trade-off maybe between the EMI performance and component size and placements of the board, as well as maybe even efficiency. And in particular, if I do have differential common mode noise issues, those suppression techniques, those mitigation techniques are quite different. We will begin talking about ways to mitigate, reducing the EMI itself. And as I mentioned just before the break, sometimes you may have to make some compromises or trade-offs. Why did you go to engineering school and become an engineer in the first place? For me, the answer to that question is I really liked making trade-offs. There's no good answer, but here's what I believe to be the best one. So sometimes you have to do that. In this case, this example is describing one way to reduce the EMI might be to reduce your switching speed and force the fundamental or other harmonics into a more friendly portion of the spectrum where you have more margin. Now, once you reduce switching speed, you are going against the whole point of the high-speed switch mode power supply to begin with, and you may be giving up efficiency or going to larger components with slightly heavier footprints and maybe paying a little bit more money for it. But maybe that's the decision you have to make. Other suppression techniques could be adding filtering. This is fairly common, and sometimes it's required. EMI filtering is not the simplest thing in the world to do, but we'll talk about later. There's a differential filtering technique. There's common mode filtering technique. The disadvantage, of course, is you're adding components. You're driving up your cost, adding component count. Nobody likes it when the bill of materials goes up, but maybe that's your only choice. Another option is to go into the layout and address some issues in the layout. Specifically with common mode noise, most of the more common issues associated with common mode noise are layout related. This is a better approach. If you can do it in the layout, it's the best approach because it's the lowest cost approach, assuming you haven't built a bunch of products yet. But so quick summary, 43. So this is the design process. And as I say on TV, we'll break it down for you. I cannot believe the number of weather forecasters who have adopted this phrase. I'm going to break it down for you. Good for you. Break it down for me. I don't get it, but I'll say it. If they're saying it, I'll say it. So we want to knock the EMI issues in the teeth. The process is we're going to have to start with a library of components. This is essential because the components have to be containing any parasitics that they have as well, and that's important. We've got to have a basic schematic design. The layout, we have to have a prototype layout. We can make adjustments to the layout, and then of course any techniques to follow up with whether filtering adjustments have to be made in the process. Electromagnetic then analysis is essential to what we're doing. The layout has to be run, the artwork has to be run through an electromagnetic solver that will extract the inherent parasitics associated with the artwork. And that includes all the different layers, all the different vias, metal thicknesses, footprints for the pads, footprints and surface mount pads for the components. Excuse me. In this slide, on the far left column, you see a schematic only. And on the top left trace, the red trace there, that's the common mode noise associated with this thing. And if you take, and as you go through your steps, you have an initial and then a final layout that you've made modifications to. You can see the step in the middle and the far right. You see the noise spectrum has been brought into compliance and actually approaching the original schematic only analysis. So that's a good example of some really good results that can be obtained. Let's talk about the requirements for the design tool. The things that we're going to need are we need a schematic layout and electromagnetic integration. We're going to be focusing on a method moment solver for convenience and speed, but you can also use a finite element solver, and we can supply that as well, and it is part of the cockpit. It's built in. The transient analysis, or SPICE type analysis, is the time domain solver, and a harmonic balanced frequency domain solver is also essential. We provide both of these. And in addition, the concept of passivity is important, and that is associated with S parameters and transit results that we run an analysis on, and maybe a measurement of electromagnetic analysis or S parameter measurement on a network analyzer. And sometimes the component results come back non-passive, and they might appear to be very, very slightly non-passive. Sometimes that's an issue with regard to calibration. There are other issues. We can address this issue, identify non-passive, and enforce passivity. All right, so I'm going to switch to a demo here real quick. Okay, good. This library model has been my backdrop, so I wouldn't forget it. So this is a common mode filter that would be used, a common mode choke, that will be used for common mode noise filtering. This TDK part is pretty popular, and it's a common part. TDK has a nice library of components, and they supply different versions of the models for them. And this is a SPICE model. which you could use, or you could use S-parameter measured data that they supply as well. But I wanted to show you this to make a point, and that is that the components that you're going to use in your schematic, whether they're resistors or capacitors, of course transistors, filters, it's really important that you use accurate models for them, because they're not just plain old lumped perfect capacitors or perfect inductors. They have parasitics. If I buy a capacitor from a surface mount component vendor, it has inherently a parasitic series inductance and series resistance associated with it. And it's important that those component parasitics be included in the analysis, because they can have big effects. And that's why component vendors have so many different product families, because some are good for some applications, and for other applications, they're a bad mistake. So in this case, the point I was trying to make with this common mode choke here is there are a lot of parasitics associated with this. Look at the SPICE model, and it's symmetric, so you could drop this part in either way. But there's a lot of content here that needs to be part of the model. And if you ignore this and you just try and model this as an ideal component, then all of the effort that you put in to the analysis and the results post-processing is not going to be very helpful, because you will have perhaps walked past a fundamentally important issue that you're never going to see, because your model doesn't incorporate the parasitics. So let's go back to the layout. And then in this navigator on the far left here, there's a bunch of different ways to be convenient in terms of sorting through the layout. But you can see the different components are different sizes. They have different footprints. And that's not just for the capacitors, but for the resistors. Don't think for a minute that resistors, surface mount resistors, don't have parasitics. They do. And but people just sometimes forget that there are issues that might come up to get you if you are not paying attention to some of the details. The details here are: go to your component vendor's website, see what kind of component model library content they have, and I bet a good amount of money they have an ADS downloadable library. We also supply library components as well that you could sort through, but your particular vendor might not be in there, or maybe some of their later parts might not be in there. So, and let's take a look at the conducted EMI test bench. So we automatically will create this test bench for you. When we run the electromagnetic analysis, you don't have to be an EM modeling expert. We ask you some simple questions. I think we need 4 pieces of information. What's your switching frequency? What's your rise and fall time? If you're not sure, err on the side of faster. And then if you have a ripple frequency in mind, enter that. And then from that information, we will collect the proper amount of frequency sampling to perform on the EM analysis. And then that gets embedded into this little guy here. There is your symbol that represents your EM extracted component-based analysis of your device. That's your switch mode power supply right there. We connect it with some labels to the test bench here. This is a conducted test bench, so you've got your source and your return lead. I'm sorry, your source and your return lead listen devices. If I push into those, the model has parameterized all of the components, so these can be fed in with different values depending on different standards that you may be running in different listen configurations. And then we want to try and replicate the EMI lab as much as possible. So that includes things like the test leads. So connected to our device under test is a 6-inch section of 10-gauge wire. So we've accommodated the loss, resistive loss, and inductance associated with that wire. And if you want to try and correlate results with EMI measurements, lab measurements, these are some of the things that you need to attend to. And so we bolted these into the test bench itself. So this configuration, you can edit it to your heart's content, but this is what we supply as part of the native test bench. Not just on the source, but also on the load. So out on the load, similarly, we've got a 10-gauge set of wires on the positive and negative portion of the load, 6 inches long. And the load itself right now is represented by a pure resistive load, but that can be as complex as you'd like it to be as well. So this load right now is a half-ohm resistor. It can take 1,000,000 watts. It won't get warm. It won't glow red. That's the nice thing about it. We parameterized the information up here in a little variable list. We pre-configured the transient solver for you, and we set it up with what we've determined by heuristics to be the best convergence time-stepping algorithms to walk you through using the EM data that was generated. In fact, we actually call this a PE version, a power electronics version of the transient solver. So the SPICE solver here is a special version, pre-configured version, optimized for power electronics. And then lastly, we have a specially configured display template that has the equations for the EMI receiver set up, the resolution bandwidth, detection mechanism, frequency bands, etc. And that will automatically populate for you. So this test bench is all done for you. It's all customizable as well, so you could make it special for something that you're doing. And I'll open that up real quick, and then we'll switch back to the presentation. All right, so what we did was we took this power supply and we turned it on from time 0, and then we let it stabilize and reach quasi-steady state, which we could have waited a longer time. I deliberately didn't wait too long. I wanted to see the conductor results before it reached complete steady state. So I'm out at a millisecond. And in particular, I can actually go to the last several cycles. So in this case, I'm looking at it's a 2 megahertz switcher. I'm looking at the last 500 cycles here of the switcher. And I'll just switch that down to, let's make that 200. So this gives you a little bit of idea that there's a whole lot of things that you can do in the post-processing to sort of zoom in on portions of the time domain waveform. And what we're looking at here are the last 200 cycles of a quasi-steady state. I stopped it at a millisecond. And you can see all kinds of different things. These are all built into the template. You can add what you want if you don't see what you need. I'm looking at about 64% efficiency. I've got 500 millivolts of load ripple. I've got 20 volts in. Supposed to be delivering 10 volts out. I'm at 9.96. And then of most interest here along the top is the FFT frequency spectrum. Total noise. I've got a CISPR 25 mask there. That's the red portion. And then we've got differential noise, and this is composite noise over here on the right. I'm sorry, my mistake. Differential noise there on the left and common mode noise on the right. This is peak measurement. And just above that are my CISPR 25 band specs. And again, this is all customizable or reconfigurable if you're using different specifications. Now, I did that deliberately. I wanted to just change things up a little bit. I don't want to. One of the things I didn't want to do was make a bunch of changes for the presentation that are different than the actual out-of-the-box example that ships with the product. So I wanted to keep things as close to the example as possible. Okay, I'll stop sharing here and go back to the presentation. Now, I showed you that TDK common mode filter, that common mode choke, and I wanted to show you that because it has a lot of parasitics associated with it, and it's important that they be modeled. So step one, component modeling. The components should have as much detail as you have available to you, or just use a vendor model, and the vendor models should have the parasitics. If you have different components you're trying to pick from, choose among, or you have different models you're trying to work with, maybe you've got a couple of vendors and they've sent you S-parameter data, you can easily set up your schematic to swap between components. We call it polymorphism, and the component models can be walked through to see which one works best, or which gives you the most faithful representation to your measurements. So now let's talk about the EMI mitigation. If you have EMI violations, in this case, bottom right spectrum, you can see you've got a significant amount of EMI above the permitted level. You start to look at and separate differential versus common mode noise, and which one do I try and address. In this case, we're going to look at the main issue in this example is differential noise, and we're going to decide, okay, let's filter it. All right, so top row, no filtering. Middle row, we have an ideal pi section filter, and it works perfectly. So that's great, and that's important. If it didn't work, then we have other problems to deal with. If my ideal circumstances don't work, I have bigger fights to address. But at the bottom, then, we've gone to a non-ideal filter, and we've made a balanced section with component parasitics associated with it. And it's filtering nicely. It's doing the job. And we have confidence in it because we modeled it well with components that have parasitics included. Problem with adding filters is if I can get away with making changes to the layout, instead, the filter is extra cost, extra component count, and also almost always will hurt your efficiency. You've paid a lot of money and put a lot of effort into being very highly efficient with this design. You don't want to throw it away with an unnecessary filter. Okay, so turns out this was a good low-loss filter. Efficiency stayed up in the 83% area, and this was a good approach, it turned out. All right, so what I showed you earlier, the test bench I showed you earlier in the demo, it was a version of what I'm showing you here on this slide 55. It was a EM-based extraction from the test bench. It incorporated the substrate stack up and all of the artwork, and that's the point of this slide. The layout can come in as an import from ODB++. So that'll include the substrate stack up, material properties, etc. This is a slightly different version of an example that we had a schematic that was working okay. We attached it to the layout, and we end up with a significant amount of common mode noise, and efficiency drops to about 72%. Those arrows, the red arrows, are rotated. They should rotate them 90 degrees clockwise in your head. So we need to add a common mode filter to that previous example, and we can use an ideal one or a physical one, like the TDK model that I showed you that had parasitics. And what happens when you use one with parasitics is you find out, it's maybe not working as well as you thought. In this case, it's doing as good a job as it can, but it's way too lossy. It's going to give away so much efficiency. Let's talk about artwork, layout parasitics. Every trace has associated with it inductance. If I run a wire, whether it's a piece of number 30 gauge wire or it's a trace, it has inductance, inherent inductance. And in the layout, it's hard to predict what that would be without running the analysis of an EM extraction. This is just giving you some rules of thumb and some basic information regarding a trace, its skin effect resistance, and also a little bit of data on a PCB via hole, a through hole via. People forget vias have inductance, and they also suffer from skin effect. All right, last poll question, quickly. Same 1 ounce copper PCB. This time, instead of a 4-inch wide trace, it's a 40 mil trace, 1 millimeter wide. What's the equivalent wire gauge for that? And while you're entering, I'll tell you the quick thing that you can do is, a lot of people don't know the AWG wire gauge is a log scale. All right? I went from 4,000 mils, which was a 12 gauge wire, to 40 mils. It's a factor of 100. My log scale of 100 is 20. So I can move 20 gauge numbers. The correct answer is 32. So what was 12 gauge at 4,000 mils, at 40 mils is a 32 gauge wire. So it gives you some perspective. 32 gauge wire is very tiny. Has a lot of loss. All right, some good guesses here. So just perspective. Trace layouts, trace runs have a lot more meaning sometimes when you think of them as wire gauges. I personally find it helpful. Filtering. You can purchase filter parts, as I showed you the TDK common mode filter. You can build your own. The choice may be simply, is the part available for the things I need it to do? Is it less expensive? Or even is it possible to do this in discrete models? Another possibility is for common mode filtering is this concept of a Y capacitor. Sometimes the Y capacitor has a third terminal for earth termination. Sometimes those parts aren't available, and you can make your own. And again, as component models for surface mount parts, inductors, capacitors, resistors, in this case, bottom example transformer, they all have parasitics associated with them, and they have frequency-dependent behavior. It's important to use the information if you know it, and also to use component vendor parts from the component vendor libraries that include this information. This is actual web page capture from that TDK part I showed you. And that's the same part. And don't forget that had a S-prime error frequency measured data. All right, so this particular slide is from my colleague Colin Warwick, who was on the phone with us today to help answer any questions. And his issue here to point out was, in this case, you have a bad layout, no filtering, you have emissions that are not meeting spec. Don't just throw an EMI filter on it without some attention to detail, because it may or may not solve the problem. But let's say it does solve the problem. But you've added to the bill of materials, you've added the cost, and you could have took a pretty good hit in efficiency, whereas on the bottom right, if you went and modified your layout, you might be able to get by with no filter or a smaller, less expensive, higher efficiency filter. All right? So attention to detail in the layout is critical, even if you feel like you can filter it. All right? So what about improving the layout? First thing to think about and to consider and keep in mind, and we do this for you automatically in the test bench, when you do the extraction in the EM analysis of the layout, you cannot just drop ground symbols all over the place in the schematic or the layout, because what they'll do is they'll tie everything to a common reference of 0 volts. And that, on a layout, that's not correct. The potential at each point on the layout is not going to be the same. Even if it's on a ground layer, it's not going to be the same. In addition, if you do something like this and drop ground symbols all over the place, you could be removing significant amounts of inductance as well. So what we do here instead is we supply a pre-configured scenario here where when you do this EM extraction in the layout, in the PE cockpit, you get this reference cover of an earth ground, which is separate from having a 0 volt potential ground on the layout. So when you probe the layout, you'll find out that the potential on all the different metal points is legitimate. Another thing associated with the layout, and trying to improve the layout, is keep in mind that you can drop impedance and significantly with shunt capacitance. Shunt capacitance can be and incorporated by widening traces and providing a coplanar waveguide type via picket structure. And then another aspect of layout improvement is simply shortening or fattening traces to reduce IR drop, paying attention to return paths, making the return paths shorter. And also, when you have capacitors involved, remember the capacitor has a parasitic shunt, it has a parasitic series inductance. That series inductance could be significant, and it could add, and you may really need to pay attention to not only the placement, but actually the component part itself and the parasitic inductance from that vendor. And as far as radiation goes, this slide is also from my colleague Colin. Radiation comes from two sources. One is an oscillating electric dipole. This field is set up when you have a dipole, and this dipole can be a tiny set of traces on your board, and depending on its size and the frequency, you could have a very significant and very efficient antenna created by accident. The other source of radiation is an oscillating magnetic dipole, i.e. a loop antenna. The effects that are associated with these two that make them good antennas are the separation distance for the dipole, the length of the dipole, and also the loop area of this loop antenna. So paying attention to this distance L, the dipole length, keeping it short, and this area, this loop area A of the loop antenna can help you clobber some of the capabilities of these as efficient radiating antennas. One way to sort of clobber a loop antenna is to create a loop that will radiate in the opposite direction effectively. And this can be done in coplanar kind of configuration. That's one of the reasons coplanar is very popular. If we have time, I'll do the demo for radiation, but this is a plot of the captured radiation at a certain frequency. And this is what's unique here is in this test bench, what we do is we attach your layout, your components, and we extract its behavior, its time domain behavior. That's FFT to the frequency domain, and all the frequency content that's in there then can be used as an antenna excitation. So while this thing is running, while it's operating in the time domain, you will see the effect of the layout and the components operating at the frequency of operation and the switching edge rates, and all the frequency content will be available for you to plot either patterns or a field strength plot versus frequency. So we'll basically virtually attach a probe and walk this probe all around your circuit and pick the highest points or points that you say, and see here's the max field strength at a certain distance, in this case 10 meters, and here's the compliance mask for you.
Okay, George, I'm going to have to cut you off here. I'm sorry, because we got too many questions.
Okay.
We have like 10 minutes left. I want to make sure we get time for questions.
Okay.
Thanks, George. We also, just so you know, we hold many free virtual events throughout the year, and we just ask you to take a couple minutes to complete the survey to the right of the screen. And there's just 3 simple questions there. Please let us know if you'd like a follow-up from us. Yes, I would like a technical expert to contact me regarding PathWave Power Electronics. Please send me a quote, or I'd like a remote demo on PathWave ADS Power Electronics bundle. Now, I want to get to some of the Q&A if I can. Yeah, George is showing that up here right away as well. You can just answer this one. And while that's on the screen, I just have a couple questions for George here. And the questions we don't get to, we will answer them, and they will be emailed to everybody as well. So I'm just going to kind of pick and choose these. George, can you do both conducted and radiated EMI?
Yes. Test bench for radiated and conducted are both built in.
Okay, great. If I don't want to use the CISPRI mask or other built-in mask, can I create a custom mask? If so, how do I do that?
It's extremely easy. It's just sort of a etch a sketch point to point. So yeah, you can do it. It's not difficult at all.
Okay, great. In a boost converter, where is the best place to put an EMI filter? The input or the output?
Colin, I have an experiential idea for this. From what I've seen on a boost converter, what I've seen is on the input, but it might depend on the topology. I don't know. There's a good answer for that.
Yeah, Chad, this is Colin here. I'd say that it depends on the situation, and the good news is that the simulator allows you to try out both, either or both, depending on what the problem is, and see the effect, and choose the most cost-effective solution. I think it really is very situational.
Okay, thank you. How do you import the PCB into ADS simulation software?
The input technique is ODB++ archive. That'll have all the layers, material properties, stack up information, geometries, and the drill files for all the vias. So that's simple, real easy.
Okay, thank you. Do you account for EMI from the lumped elements, like an inductor, or just the PCB?
Most of the results, most of the EMI is going to come from the actual PCB itself. So at this time, just the PCB.
Will using faster edges not increase the signal spectrum? That is, will we have higher frequency noise?
Most general answer would be it depends. Most probably yes, but you can experiment with the different edges. You can do the extraction of the board with an assumption of higher edge speeds, but then so that the information will be there for you to experiment with, and then in the setup of the simulation, you can change your edge speeds and see what the results are, and you can see the effects.
Okay, thank you. The next one, by adjusting the rise and fall, can power losses in the switch improve?
Absolutely. And that's another thing that, as I said earlier, run your EM extraction with the higher edge speeds, and that way the parasitics will all be incorporated for you to experiment with those different ranges, and you can plot the efficiency. It comes out in one of the answers we give as part of the test bench.
Okay. The next question. Isn't an LSIN an LP filter from supply to the DUT and a high-pass filter from DUT to the test equipment?
Is the question that isn't it the thing you said? And if that's the correct interpretation, the answer is yes. Okay.
And I just reminded, make sure you fill out the survey in the right hand, by the way. On slide 32, the circuit looks like a low-pass filter rather than a high-pass filter. Usually there's a capacitor blocking DC when it's a high-pass. Do you have any comment on that? You want to go back to slide 32, if you can? They said the circuit looks like a low-pass filter instead of a high-pass. The question is, usually there's a cap blocking DC when it's a high-pass. Do you have any comment on this?
Well, I definitely don't want a series cap here because I do have to pass DC. And so remember, this is between my supply and my DUT. So I'm attaching a battery to the device. I need DC path. But this does have a high-pass topology. So I personally would stick with the specs because the specs describe exactly what this has to be in the values. There's nothing fancy about this. These are purchase parts.
I think the confusion is that it's a high pass between the switching circuit and the spectrum analyzer. But it's a low pass between the switching circuit and the mains. You have to specify from what to what. I think that's the confusion. So it depends on which terminal you're talking about. Is it the output, the input to the output, or the output to the spectrum analyzer?
Yeah, you're exactly right. Yeah. It's a high pass to the spec in.
Okay, I'm going to ask two more questions, and then we're going to have to call it quits. But as I said, we will answer all the questions that we have in the Q&A by email, so please keep putting your questions in there. Next one is, can more complex loads be simulated, such as LEDs?
Absolutely. If you can describe the load electrically, we'll simulate it.
Okay. And then the last question, what about loads which have heat sinking, which provides a path for common mode noise? How does that get included in the simulation?
I don't, Colin, I don't understand yeah,
I didn't understand that question. Is it an electrical path through the heatsink or a thermal path? I mean, obviously, an electrical path is trivial to model, but if it's a thermal path, I didn't understand the question. Maybe we can take it offline with the question, and we need to ask some questions. Yeah, let's take it offline.
Okay. All right. That's all we have time for questions today. Thank you all for attending Reducing EMI Interference in Switch Mode Power Supplies, brought to you by Keysight and ElectroRet. Please visit us at keysight.com/events for all upcoming events. The copyright of the presentation is owned by Keysight. I'm Jack Field. Thank you for joining us, and everybody have a great, safe day.